Welcome everybody to the British Astronomical Association Hydrogen Line meeting this evening on Monday the 6th of July 2026. It's lovely to see you all here. As always, these meetings are recorded and they will be available on the British Astronomical Association YouTube channel in a couple of days. Tonight we have Jason Burnfield giving us a couple of talks. Jason will tell us all about himself, but basically he's highly experienced in radio astronomy, and he's been doing some incredible stuff with making his own telescopes. So this should be a really fantastic set of talks. He's also been doing some observations with myself on the 20-metre Skynet dish, which is a Greenbank observatory, and anybody that's a member of the Society of Amateur Radio Astronomers gets access to that dish. And it's amazing what you can do with that, and I can recommend anyone who is a member to have a go at that. And if you're not a member, to consider joining SARA. It's only about $20 a year in order to have a go, because it's well worth it. Plus their meetings are fantastic. Anyway, I will pass the floor over to yourself, Jason.
Can I interrupt, Andrew?
Oh, yeah, sure.
A message on my screen. Paul Heron, admit. It's gone.
Oh, yeah, so no, I've already admitted Paul. It's okay. He was here, he went, and he's come back again. Okay. Yeah, so I thank you very much for letting me know, Mark. Yeah, okay. The floor's all yours, Jason.
All right, I'm sharing my screen here.
So sorry, Jason, just to say, I'm going to just mute everybody. It's easier for me to press mute all. You might need to unmute yourself again, Jason.
Okay. How about now? Can you hear me?
We can hear you well. And we can see your presentation as well.
Okay, so I'm going to put it in presentation mode here.
At the moment, we can actually see you're on presenter mode, so we can see the first slide and we can see the next slide on the right-hand side. So you might want to change it to display mode.
I'm going to stop sharing for a minute, and I'm going to reshare and choose. Let's see, I'm going to put this over here. There we go. And I'm going to choose.
When you do start your presentation, can you tell everybody a little bit about yourself?
Sure. Okay.
We have a cat at the moment.
Yeah. Okay. Good.
Or the back end of a cat, anyway. Yes, we can see a slide
there
now.
We go.
Adventures in Portable Dish Design.
What I wanted to do is get you guys up on one screen and the presentation on the other screen. All right. So, yeah, my name is Jason Burnfield. I've been involved with the Society of Amateur Radio Astronomers for a few years now. I think I started in like 2023, I think, 2023. But I actually started experimenting with hydrogen detection in, I think, 2021, maybe. Oh yeah, I think I'll get into that in this presentation. Can everybody excuse me for a minute? I've got a call coming in from work. Just a second here.
Yeah, that's fine. So, Paul, would you like to perhaps make your announcements now?
Yes, okay. I joined this group earlier in the year, probably April, May time, and I was saying that my plan was to actually get some first light during the year. Well, things have progressed slowly, but progressing, and I've now built the Cantana and mounted it onto the dish, and in the next fortnight I'll probably download Ezra software and start having a look at some data acquisition. So maybe at the next meeting I'll have some of the very first data, and as we come up to that point, I'll probably have loads of questions. I haven't downloaded Esri yet, but I have looked at some of the, well, pretty much all of the most excellent videos. So that's what I was going to say. The other thing was, just very briefly, until Jason gets back, things are progressing very nicely for the day conference, the BAA Amateur Radio Day Conference. So we have got an H-Line session, which Andy Thornett is going to host. And if there's anybody on the call tonight that looks like they're going to be in Sherwood, at the Sherwood Observatory at the conference at the beginning of October the 3rd, and you've got some data or some design ideas, do let us know. We've got 1 or 2 slots free, but they're filling up pretty fast. But if there's anybody here that's going to be at that meeting and wants to share, then do be in touch with me and or Andy Thornett. That's it. That's all from me.
Oh, marvellous. Thanks very much, Paul.
All right, guys, I'm back. Yeah, we're still moving antennas here, and so sometimes I get calls to do checkouts on things. But honestly, I've got my email up, so they can get to me through email if they need to. As far as I'm concerned, this meeting is officially on the clock too, so I'm just going to ignore the calls and stay on this presentation. So
say, Jason, it doesn't matter if you have to go for a call. Don't worry about it. I can start cycling through other people quite easily while you're on your calls. So don't worry.
Okay. Yeah, it's not urgent though. If it was something super urgent, they would reach out to me on multiple multiple channels. Yeah, so I got involved in SARA about 2 years after I started experimenting with radio astronomy in the backyard, and this was back when I lived in Indiana. Then in summer of 2024, in August of 2024, I actually got to attend the Eastern Conference at Green Bay, and just so happens that I had applied to a job at the National Radio Astronomy Observatory the month before that conference. And when I got back from the conference, I began to get a series of interviews for that job. And by the end of calendar year 2024, I had secured a full-time job working in radio astronomy, actually. Although I'm not an astronomer, I'm an electrical engineer. I'm supporting the receiver hardware. So I get to work on the very large array and the very long baseline array. So I moved to Socorro, New Mexico, and yeah, I'm getting to work on some pretty cool stuff. So that's a little bit of background on me, and now I'll just jump right into this first presentation if everybody's good with that. So this first one, just to preface these presentations are ones that I will be presenting at the Eastern Conference, and you guys get a sneak preview. So, and I believe they're pretty much complete now. I plan on submitting them this week, the final versions. So the first one is I've entitled Adventures in Portable Dish Design and Construction, and I'm just going to jump right in here. So let's see if I can. Oh, there we go. So starting way back in 2021, my original experiment was to build a corner cube reflector antenna, and I used an RTL SDR version 3, I think, and a Sawbird H1 LNA, and I detected the hydrogen line from the Milky Way for the first time. Then I began the quest for more aperture. I became convinced that I wanted to try to go after the hydrogen signal from Messier 31, and so I thought, yeah, I'm going to definitely need more aperture for this. So my first attempt to build a dish, you're seeing here, it was basically a kind of a freestanding structure that I could put up and take down, but it had some drawbacks. It could only point to zenith, and it was really cumbersome to assemble and disassemble. But it did turn out to be a good proof of concept. So then I began a two-year journey of design, rebuilding, redesigning, and rebuilding, and incorporating all my lessons learned. I eventually settled on an inverted umbrella design. So what I would do is I would use plywood to plywood ribs to basically set the parabolic profile, and then I would have a sliding ring and these vertical poles, and it would fold up like an umbrella. I eventually shortened the focal length to diameter, the F to D ratio, from half to 0.35. I was looking at some experimental research by some amateurs who had shown how different types of feeds perform with different parameter designs for dishes, and I found that smaller dishes tended to perform better if you had a shorter focal ratio. Then I changed the reflector material from aluminum and copper tape to aluminum window screening. And I also moved the reflector to the front of the ribs instead of the back of the ribs, so the ribs weren't actually obscuring the signal. And I added some shielding around the edge to cut down on thermal noise from the ground. And then eventually I switched the reflector material to this stuff called Faraday fabric, and that worked really well. It was sort of like tent material, but it was made from nickel copper alloy. It was inexpensive, and it performed really well. And this is the design. This is the version of the design that I ended up first detecting M31 and M33 with in March of 2024. This is the actual setup that I succeeded with my first detection. I made a few adjustments after that and got improved results. And but this dish the wood wasn't weatherproofed, so eventually I had to scrap it. And I built a slightly smaller version that was weatherproofed. It was about 2.5 meters, and it was easier to transport. And that's the one that I brought with me in the back seat of the car on the drive across the country when I moved to New Mexico. Unfortunately, the Faraday fabric and the flimsy structure of that 2.5 meter dish just couldn't handle the desert wind. And about a month after I moved here, it got pretty much destroyed. And so I was like, I decided it was time to go bigger and better. So this photo of me is actually my next attempt. And I was going to build this was supposed to be a 3.5 meter dish. And I got as far as building the physical structure. And in the meantime, when I laid out the plywood and marked out the plywood for the 3.5 meter dish, I had enough scrap wood left over that I decided to also build a smaller 1.5 meter mini dish. And I kind of ended up taking a detour and focusing on the mini dish for a while because it was just so, it was easier to work with, and I felt like I could I could work out all of the construction details on a smaller scale, and then when I went to build the bigger one, I would have been able to figure out a lot of the practical issues. I really was pleased with how my mini dish turned out. So now I'm gonna focus in on the design and construction of the mini dish itself. So it's an upside down umbrella. with the profile ribs. Has vertical dowels that hold the feed and a sliding ring. The sliding ring is attached to the ribs by PVC supports, basically small PVC pipes, and it opens and closes like an umbrella. I started with a design tool that I made in Excel that allows you to type in certain parameters and it generates coordinates for the profile ribs that then you can mark out on plywood by hand. And so it's kind of a low-tech design tool that allows somebody who's just doing this as a hobby to, with very few, professional tools, to be able to lay out, design, and actually construct the dish. So I typed in the FD ratio I wanted and the number of ribs and the rib attachment point and ring position, and then it generated all of the other information for me. And I even made it, I built in a little plotting, I used a plotting tool to basically make a kind of a simple line diagram of what the dish would look like to scale, so you can get some idea of what the dimensions are. So that's how I got started with the design. Then once I had that, then I marked out the ribs on sheets of plywood, and then I had a friend of mine in town who does woodworking do the cutting and sanding for me, because I have a small scroll saw, but it's not very capable, and it doesn't really handle large pieces well. And plus, my skill level in cutting out large curved pieces with any kind of accuracy is not it's not well. So I was like, I'll just pay my buddy to do it for me. So that's what I did. Once I got the ribs back from my friend, I drilled the holes for the support attachments in the ribs, and I cut out and drilled the PVC supports. Then I assembled the structure using zip ties and machine screws and washers and nuts. And then I attached a nylon rope or a cord around the edges of the ribs to evenly space them and add structural support. So it keeps this, when it opens, it puts this rope in tension, and it makes the structure pretty rigid. I checked to make sure it folds up smoothly, and the feet of the tripod are made from big steel bolts, basically. Weatherproof the plywood with some weatherproofing, clear gloss weatherproofing, just to protect it from the elements. I found with my previous dish that worked well, and I didn't have any problems with the wood deteriorating that way. The dish is portable, so I take it down if there's really bad weather, and I don't leave it out in the rain or anything, but it is still good to weatherproof the wood if you want it to last. The reflective surface is aluminum window screening, and it's attached with upholstery staples. I found that window screening is permeable to the wind here, and it doesn't act like a giant sail like the Faraday fabric does. I also made sure all the gaps were covered with window screening, so the holes that I made for the poles to stick through, and also the holes for the supports, I covered with extra window screening to prevent any ground noise from creeping in. I use nylon pegs to lock the ring in its open position, and there's nylon screws underneath that set the floor, so when I push it down, it has a stop. And then I cut notches in the dowels to lock the feet in position, so it basically just clicks into place. The dowels hold it firmly, so it's easy to install and uninstall. And the dish is secured in place during my observations using nylon cord or rope attached to bricks and paving stones. And I set my elevation using books. paperback books. So the final design parameters turned out to be the diameter was 1.54 meters, or 1.54 meters, and the focal ratio is 0.35. I had 18 ribs, and the half power beam width is about 11.5 degrees. So then I went to testing it out. So the great thing about the mini dish is it's small enough for me to lift by myself. And so I was actually able to do ground sky tests because I could actually pick it up and point it at the ground. And so I did that. I pointed it at the ground, collected a few minutes of data, then pointed it at the sky, collected a few minutes of data. Then I pointed it at the sun, which was low in the west when I did this test. And I just did that a few times, and I got some sense of its performance. So my ground to sky delta was just over 3.5 dB to about 3.7 dB in the second test. And then the difference between sun and cold sky was 5.5 dB. So I was fairly pleased with that for the small aperture. I also captured zenith transits of the Milky Way, so this shows both transits when pointed at zenith at my latitude, and that performed very well. It was around 1.5 dB above background for both. And here's a Milky Way transit that I captured during an M33 drift scan observation. And you can see the peak is, I've got it normalized to 0. And so the background, or the peak was not quite 1.5 decibels above background. And then this was the result after 12 days of drift scanning M33, and you can clearly see the spectral profile of M33. So I was actually able to detect M33 with the small dish, which was surprising and satisfying. So then I moved on to the bigger dish. To save a little time and money, I decided to reuse the base and dowels and sliding ring from my original 2.5 meter dish. I got as far as the assembly of the frame, and then I realized that the design didn't scale up really well, and it was too flimsy and difficult to maneuver. I had trouble with the ribs cracking on me, and I had to keep repairing them. So I finally scrapped it and went back to the drawing board. So I designed a new dish with a diameter of 2.13 meters, with 21 ribs, and I made it with wider, heavier duty plywood, and I made the ribs thicker. I increased them from 2 to 3 inches wide, and I increased my my plywood to 3/4 inch plywood, and it made a huge difference. But then I also planned that main dish with a focal ratio of 0.42, so that I could then add extensions later that could bolt on to the edges, that would basically continue the profile. The focal ratio would be reduced to 0.27, but I can increase my aperture to 3.3 meters. And so basically it's an expandable design. So then I made poster board templates to trace out the parts onto the plywood, so I wouldn't have to keep measuring. Before I would just measure and mark each one separately on the plywood, and I was like, why am I doing this to myself? I could just measure it once on these plywood templates, or on these poster board templates, and then just lay them out on the wood and trace it. So that's what I ended up doing. Every time I've built and rebuilt these, I've learned things that make the next build easier. So I reused the dowels and the PVC supports from the previous attempt, but the sliding ring I had to redo because I decreased my number of ribs from 24 to 21. I also built an entirely new base that was thicker and more robust. So this shows all of the plywood marked and ready to cut out. I drilled the holes in the base and the sliding ring and installed the tripod feet. I had to countersink the top holes of the base so that the nuts would fit because the base was a lot thicker, and so the threaded part of the bolts didn't stick through far enough, so I had to actually countersink them, which also had the secondary advantage that the top of those nuts were recessed down into the top of the base, so they didn't interfere with the ribs when the dish was open. I glued the dowels into the base and fit the sliding ring in the feed into the open position just to kind of see, kind of get a test fit and kind of see how it was fitting, how rigid it was. I was pleased with the structural stability and rigidity of the design. I had my friend cut out these as well, and I got them back after a week or so. And then I drilled the holes and trimmed the ends. And once I had everything ready to assemble, then I started my assembly. And so I assembled it very similar to the mini dish. It's almost exactly the same. It's pretty much identical in design. Made sure it opened and closed properly, and that everything worked well. And once the structure was complete, then I covered it with aluminum window screening. And then it was finally finished, and I was ready to test it. So I did a sun scan to measure the half-power beam width, and I got a beam width measurement of 7.8 degrees, which was actually about it was slightly better than what my design tool predicted. So I was really happy with that. And then I did get a strong Milky Way hydrogen line detection. And I also did a drift scan of M33, and this is 2 days worth of drift scanning M33. So I'm pretty pleased with how it's performing. So that is my my presentation on. Let's see here. Why is screen? Oh, there we go. Okay. So that is the end of my presentation on my dish design. One of the things that I'm going to do, I did document the dish build on video, and I have it uploaded to my YouTube channel. And what I was going to do is go ahead and paste a link to that in the chat, so anybody who's interested in checking that out can have access to it. So I've just put that in the chat if anybody wants to check that out either now or later. Is there any questions or comments on this presentation? I will say I have made my Excel design tool for this dish design is available on Andrew Thornett's Litchfield Observatory page. It's just an Excel spreadsheet. And I have it locked down, but not password protected. So that way, if you just want to use it and you don't want to accidentally delete some of the the calculation cells, it's protected. So you can only edit the ones where the data entry is. But if you do want to modify it or edit it, you can simply turn off the protection. There's no password protection or anything. So so anybody who wants to try their hand at designing and building one of their own, feel free to use that tool. So,
hey Jason, this is Bob. This is super interesting. I recently tried to build a 2-meter dish out of aluminum, and I failed. So I'm looking at alternatives, but I have access to a pretty radio-free zone out in the country, but I need it to be portable. So I'm super interested in the idea of a portable antenna like this. Does the aluminum window screening, does it fold toward the center, or does it fold toward the outer part of the umbrella when you fold it out?
Actually, I'll go ahead and go back to the presentation for a minute, because there's a picture of it, I believe, on the smaller one. I'm going to share my screen once again, but I'm not going to put it in presentation mode. I'm just going to
Yeah, that's fine.
do it like this. But I believe... Oh, wait. This is my next presentation. But you can see the picture of it folded up. It folds outward.
Okay.
When it's folded up. And I found that it's flexible enough that it bends in a nice arc, and it doesn't really it creases a little bit, but not too bad. I mean, I find that was one of my concerns, is that it would permanently crease, and it would mess up the surface smoothness. And it does crease a little bit, but honestly, it's really easy to fix that when you open it. It's pretty taut, and once you open it, if you find creases, you can just run your hand down the crease, and it pretty much takes it out like you're ironing a shirt or something, you know. And honestly, the creases don't make that much difference anyway, because at L-band, the surface accuracy requirements are not insanely tight. It will reduce your efficiency a little bit, but honestly, it performs very well without too much messing with it. So, and for the ease of use and the fact that you can put it up or take it down in 5 minutes and keep it out of the rain, it can't be beat. I really like it. Yeah.
What does it weigh?
Good question. I've not weighed it. I would estimate the smaller one, which is the 1.5 meter, probably somewhere around maybe 35 to 40 pounds. I can pick it up easily. It may not. That may be overestimating it. The bigger one is quite a bit heavier. I would say it's probably over 50 pounds.
Okay. And you're using a loop feed up at the top? Is that right?
Yeah. It's a cake pan with a circular loop just attached to an SMA connector that's bulkhead mounted to the bottom of the pan.
Yep.
So, yep.
Cool.
Can I ask a question, Jason? It's Mark here in the UK. Just two questions. How is the screen reflector attached to the plywood plywood pieces? It's glued.
It's attached with staples. It's upholstery staples. And I just have one of those cheap spring-loaded staple guns that you buy at the hardware store.
Okay.
Yeah. Works really well.
Sorry, another question. The feed from your pickup, the loop antenna, is that running by LMR 400 type coaxial cable?
Not sure. It's been a while. I bought it a couple years ago. I know it's rated. I know it's rated
LMR
for
400 because I understood it's very low loss, but then the downside is it's pretty rigid.
Yeah, no, this is, I think this is about, I think it's about 25 feet, maybe, of cable.
Yeah.
What would that be in meters?
About 8 meters.
Yeah, so, and I believe the loss when I measured on my, at L-band, the loss was about 6 dB, so it wasn't too bad. And honestly, it doesn't really matter too much because of the fact that it's after the LNA, and I've got like 40 dB of gain on that LNA. So.
And did you power the Sawbird from the USB port on the computer?
I actually power it. I'm using an AirSpy Mini as my SDR, and it has a bias T built in, so I power it through the actual coax cable.
Right.
But it does have a USB-C port on it. It's one of the newer ones that has a USB-C port, which is for power. And I have powered it through that before when I'm using my Smart T, which doesn't have a bias T. So both work, but it's simpler if I can use the bias T because there's just less cables to deal with.
Okay. And the power source is like, was that battery?
No, I actually used a small power block for charging my phone, and just had a long cable, a long USB cable. So in an extension cord laying on the ground, I think. So
and how long was
I didn't have
scan?
much trouble with RFI either with that, so that was
in the desert.
Well. Good.
How long was the drift scan? Or what time period?
For M33, let's see, how long was it? It was just under an hour. I think it was 55 minutes, maybe 54 minutes.
Okay.
With the 11.5 degree beam width at that declination, I think it was about 54 minutes. With my larger dish, it's only 35 minutes because its beam width is only about almost 8 degrees. So.
Okay, thanks very much.
Yep.
Hi, Jason. Here is Francesco. I want to ask you, the aluminum windows screening is a single piece or maybe different petals?
It's definitely different pieces. In fact, I had to go back to the hardware store to buy more rolls halfway through. I got almost done and I ran out. But what I'll do is I'll cut. I started in the center, and actually, if you watch the video playlist that I have, I show the whole process kind of step by step. But I start in the center, and what I did is I cut out a circular panel that overlaps the ribs just a little bit. But then I had to cut out slits and holes to put it around the poles. And then I laid it in there and stapled it on. And then I would start working out from there. But I had to do it in sections. So,
Yes.
And my main concern, one of the issues, and I think you can see it on. I have to go back to my other presentation. Let's see here. I'm going to pull up this. I'm still sharing my screen, correct?
Yes, you are. Yeah.
Yeah.
Okay, good. Let me see. Yeah, I'll show it completely. So I'm going to zoom in on this. So I put the circular panel in first. Can everybody see my cursor?
Mm-hmm.
Okay, good. So the circular panel, and there were slits cut out on the 3 sides to fit it around the poles, and then small holes to fit around the poles. Then I would put in these panels in between from the center out to about here, but I had to leave an opening for the structural supports to fit through, and those rotate as it folds, so I had to make sure there was enough clearance for it to rotate without tearing the covering. And this is something I learned in a previous build. So there's these little openings that I left, and then what I would do is I would try to cover the outermost portion with a single custom fit section for each section to try to make it nice and smooth and even, because honestly the outer edge is where it's most important, right? That's where the most of your surface area is. And then what I did after I finished the main surface is each of these openings where the structural members fit through, I put strips of window screening on the backside to cover those holes to prevent any ground noise from leaking through. Because as you know, the ground is at like 300 degrees Kelvin, and the sky is in, you know, around 10 degrees Kelvin, and so you don't, if you let the ground seep through, you actually get interference from the ground that's fairly significant. So that's another reason why I go for a shorter focal ratio, because that tends to bury the feed deeper into the dish, and it tends to prevent ground spillover, which causes a lot of interference. And I found that does remarkably well to work. It works remarkably well to boost the performance of the dish.
Yes, Jason, and the various pieces are tied together with the upholstery nails, or you provided another sort of connection between the different pieces to be electrically connected?
Oh yeah, so they just overlap by about 3/4 of an inch or so, by maybe 1.5 centimeters of overlap on each one. And because I made sure that I purchased the bare aluminum window screening, not the anodized type, and so it's conductive. So as long as it overlaps, they form a very good electrical connection between each piece.
Thank you, Jason. Very interesting. Thank you.
Yep.
I have a quick question, and
Oh, yeah.
I note that you abandoned the idea of having the ribs inside the dish. I'm not quite sure why, because I don't think it should affect the reception, should it? And mechanically, it seems a much better idea.
I think it affects it slightly. It probably is not as big of a deal as maybe I originally thought. But also it depends on the weather too, because if the wood absorbs moisture, it becomes a lot more lossy too. Although I have weatherproofed the wood fairly well, so it stays fairly dry. And also I live in the desert, but in my original location, I lived in southern Indiana, which is fairly humid. So, but it also makes it easier to attach. Other than the fact that I have to account for the structural supports, for the rest of it makes it a lot easier to attach it to the structure, because you can just lay it on and then staple it. Where if I put it on the other side, I'd have to be underneath it. And, but honestly, I don't think it would make a huge difference. To be quite honest, I think it would be about the same.
Okay, thank you.
Hey Andrew, so am I good to go to roll into my second presentation now?
Do you mind if I just ask one of the members to speak if they would like to, because I know they need need to pop up. There's one person who needs to leave at 9 o'clock. That's John. John, is there anything that you would like to talk about? We have 10 minutes before 9 o'clock, so give the floor to yourself now, and then when you've finished, take as long as you want, and then we can pass back to Jason again.
I can actually probably wait a little bit longer than 9. But if you want me to go now, that's fine by me.
Why not? It gives a bit of a commercial break between Jason's
all right, then.
video discussions. Go for it.
All right, well, I'm attempting to, I would be attempting to share my screen, except that I've got both screens, let's see. Okay, good. Share, we go. All right, I think that I've shared my screen. You should see a title slide with noctilucent clouds and...
yes, we can.
And some script. Okay. So this is a brief update on a long talk, perhaps overly long talk that I gave on the 1st of June. Hopefully this is brief, as I say. So last time, last time I covered, I'm a beginner with this, I covered construction of a Yagi antenna, talked about antenna characteristics and the physical setup of the acquisition, something a little bit about the acquisition software, and quite a lot on issues that I'd had, first of all with Windows and then with my RTL SDR. And then I went through some parameter setting experiments which I undertook, and talked about processing software and introduced my own software for QCing the data that I'm getting. And then we had talks about some other things like the radio frequency interference that I see from time to time. So this is a bit of an update. After that meeting, I had long correspondence with Alex Pettit about software, and he really wanted me to go away from Ezra and to use the SDR hash IF average, and I didn't really feel that I could field those questions without actually having another go at looking at SDR hash and IVF. Well, I mean, long and short of it, I just don't like it for a number of reasons. First of all, it doesn't switch between your signal frequency and any reference frequency if you want to use a reference frequency. And it seems to be fixed at 256 samples per trace, and I felt, for reasons that I gave in the last talk, that more was better. It does accumulate a certain number of spectra, but there's a setting for that, but it doesn't seem to actually change the number that are accumulated. I found the whole setup cumbersome, really, with using sliders rather than inputting numbers into a configuration text file or something like that. No metadata is recorded in the output files, and this is something that I feel rather strongly about, actually. I think that any acquisition should include metadata, useful metadata. Well, for example, the location of the antenna, which direction it's pointing, what the frequency is used, all that sort of stuff, so that subsequent software can look at it and perhaps select particular files for particular processing. You only get you get one file per trace instead of one file per day, and that's not a big deal, but it's an extra thing to have to cope with. One of the positives is that it does have a sophisticated background removal, and by that I mean the removal of this smooth acquisition spectral background, really, I suppose it is, caused, I think, by the anti-alias filters in the SDR. But it's a black box, I don't know how it works, and I feel that it ought to be possible to apply something similar in post-processing, and I have actually got some ideas for doing that, though I haven't started to look at it. The long and short of it is Ezra, the collecting software, is working well for me, and I added one or two things to improve the metadata handling, and I don't really see a reason for changing. Anyway, these two spectra sort of are for the same acquisition, and you get, because I'm running it, I think it's 496 samples per trace, you get a lot more detail, and that makes it easier to remove spikes like this. So that was number one on the item.
John, may I make a point on Ezra?
Yeah, go on.
Yes, indeed, it does have the background removal. Yes, which removes the slope of the frequency spectrum and things like that. But Ezra simply does that later on as well. So you can do it early or you can do it later. And I thought I'd use the CPU cycles later. Thank you.
Okay, fair enough. But I don't think there's anything in Easy Coal which does that, except by using the reference trace.
Exactly right. Easy call
Right,
is
okay,
busy collecting samples. That's its priority.
Yeah, okay. Okay. Talking about the application of reference traces, there was some discussion at the end of last meeting about what you should do. And I must say I went ahead and used the ratio so that you divide the signal data by the reference to get what you want for later processing. But somebody said, oh, I think it was you, Ted, who said, well, shouldn't you use subtraction? And I didn't think so, but I hadn't thought about it very strongly. I think subtraction is correct if you want to correct for a change in extra power, one way or another. For example, if you've got thermal background noise, there seems to be quite a lot of discussion about that, and if that changes, then maybe you want to use subtraction. But in our case, we have the reference and the signal data going through the same channels, and they have very much the same background characteristics in the spectral domain. So I think that dividing is the better thing to do. Subtraction would work if the reference and the signal data were exactly the same amplitude, but they're not. So if there's a constant factor not equal to 1, and that's due to, for example, the antenna and the LNA and all the other sort of stuff that is in there, then I think ratio is the way to go. But as ever, the proof of the pudding is in the results. So what I did was I added a subtract option to my program so that I could compare both methods, and this is the result. So on the left, you have the ratio option, and on the right you have the subtract option. And where the ratio option really gains is at the edges of the spectrum, and by argument I think that it must be better in the central part as well. The ratio option works very well with other things that I have in the program, this mean and level, for example, and I think you get a cleaner result that way. You don't have this smudge of extra energy down here and here that you do in the subtraction option. So I've convinced myself that ratioing is the way to go, and that's what if you're using reference traces, that's the thing to do.
Sorry, John,
Rob,
can I just ask you, when you say ratioing, are you saying the same as division?
Yes.
So dividing
Exactly.
by the reference trace?
Yes.
Okay, forgive me. Okay, thank you.
Yes. Signal divided by reference.
So that would be the same that's in easy call, the option to divide, yeah.
Yes, that's right, because actually in easy call for display only, I think you have both the subtract and the ratioing options.
Yes, but it doesn't go into the data itself. It's
No,
just for
that's right.
presentation
That's just for display. Yeah.
Yeah, I think that's because, if I understand correctly, and Ted, correct me if I'm wrong, originally Ezra has been designed for the combination of EasyCull and EasyCon. The two together. I mean, there's nothing wrong with using EasyCull on its own to collect data, but I think the original idea is to use EasyCull, then you use EasyCon, which adds those extra functionality to allow the sort of post-processing of the data.
I would just, with easy call the collector, I would just try not to modify the data as much as possible. I want just pure data, and then let's do analysis later. Thanks.
Yeah, and I completely agree with that way of working. Okay, I had, as I reported, repeated failures of the RTL SDR log 4 units that I purchased originally. I think I must have seen 4 of them, and at one time or another, each one of them failed, although one came back to life again later. Luckily, I bought most of them on Amazon, and I could return most of them. Anyway, the symptoms of a faulty trace are shown on the right-hand side, and that's just rubbish, and it varies from trace to trace, whereas what you should be seeing is something much more like this on the left. Anyway, there was a bit of chit-chat on the amongst a number of people, and somebody said use an NSDR Smart T, and indeed that's what I've got. I've got that in now. It has a slightly different response, particularly the peak near to 0 hertz is much more pointy, and I haven't found a way of really satisfactorily getting rid of the spikes, although I'm sure I can do that, because the spikes themselves are slightly wider than they were in the RTL SDR comp. But that's, I think, is a minor issue which I'm sure I can get around later when I get around to it. So, yes, okay, so this is through my program. The one on the right is a disappointment, because I have discovered in doing all this work that my leveling isn't working as it should do under some circumstances. But nevertheless, I'm pleased with the NESDR, the Newelec equipment. And, oh, gone the wrong way. Oh, that must be a cut and paste thing. Sorry about that. Anyway, currently, I've come pretty much to the end now. Currently, I'm acquiring data continuously, and I have not had any reliability issues with the new SDR. So I'm pleased with that. It's quite a growing to-do list. I need to fix some issues with my program, that should be EZ Col QC. I need to improve the spike elimination for the new SDRs that I'm using. The mean and level option isn't working correctly for some rather obscure reason, but I need to add some other things. For example, local standard of rest correction, and the axis annotation could be better. Real time, for example, and I think hertz for the vertical axis, or perhaps a Doppler shift for the vertical axis. I have had in mind for a long time some sort of alternative background removal process, not requiring reference data, like SDR hashes plus IF average, but that's only conceptualized at the moment. So then I need to take my data to the next stage, and as I said in the closing remarks last time, I'm undecided as to whether to use Ezra or write some more software myself. And I've got a question: is there other software around? I think there must be somewhere.
There's several for collecting.
Yeah.
Really not analysis, though.
No, I'm looking at the analysis stage now.
You and I are analyzing more than what was available before us.
Okay. Yeah. Okay. I think I'm going to look at Ezra first. And I might need some help with that, Ted, if you wouldn't mind.
Yeah, what I would say on that too is, as far as analysis goes, what I've seen is there's pretty sparse availability of tools for amateurs. In the professional stuff, the learning curve is so steep. There's just so much more involved that it's basically Ted and those of us that are doing things on our own are kind of filling a gap in the amateur world where there's just not anything available at the more basic level that we're trying to work at, you know. So.
Okay, thanks for that. And then lastly, I've got to get something ready for the September meeting, which I think that I'm the featured talker, aren't I? Isn't that right, Andy?
Sorry. Yeah, apologies. Yeah, Paul sent something out, I think, that mentioned you. So yeah, you volunteered.
I was volunteered.
You were volunteered. Well, the problem,
yes, okay.
the problem
I
is.
think I've probably blown practically everything I've got to say. Certainly for the moment, I've got to think of something new. Perhaps I better do some software writing.
Is it interferometry you're speaking on? Is that right? Is that you that's speaking on interferometry or somebody else?
Oh, somebody else speaking on interferometry.
Oh, right, okay. No. I said I couldn't remember whether it was yourself that was down for interferometry or somebody else.
No, it's not me.
All right. Oh, what is it that you're down for in September?
Well, I think just telling you all the stuff that I've already told you.
Oh, I see. Okay, yeah, okay, right, fair enough. Yeah. Oh, you mean in this group? You mean?
Yes.
Oh, fair enough. Sorry, forgive me. Apologies. Now I get myself confused. I thought you were talking about the day conference, the BAA day conference. My apologies.
No, I haven't decided definitely to go for the October conference. I probably will, actually. I think it'd be fun.
Yeah, no, sorry. No, I do a good job of volunteering people. Sorry about that. But thanks for saying yes. Yeah. So yeah, please, yeah, you can go through the whole lot. Yeah.
Well, that's it. If there are any final questions, I'll be pleased to try and field them.
Can I just make one comment before people ask questions, which is for the sake, I'm sure people here know this, but it's for the sake of the video as much as anything else for people that are watching this. When you saw one, can you show again that slide which showed the, I think, it's on there, but if you go back to where that one on the bottom right or something similar to it occupies the whole screen, I think you had at one point. Did you? Yeah, that'll do.
Yeah.
That'll do. And you pointed to the green dotted line and you said around 0 hertz, and it was more spiky at 0 hertz. I just wanted to explain to people that that sounds inaccurate because, of course, on the horizontal axis it doesn't say 0 hertz. It says somewhere close to 1420.5. In fact, the dotted line represents the tuning line, which is the hydrogen line, the 1420.405 hertz. So why did John say 0 hertz? Well, the reason is that software-defined radios do not pass on the frequency from the radio to the computer, so that they actually pass on a frequency which is plus or minus half the bandwidth from 0. So at that dotted line, they will actually say the frequency is 0, and if it's 2.4 megahertz, for example, which is standard in these two SDRs, you'd be 1.2 megahertz either side of that. And then in the either in your processing stage or in the graph at the end, you add back the frequency that you know you were using to show it on the graph. So that explains that difference. So thank you for giving me the time just to mention that to people.
That's okay.
There is an X scale at the top.
There is indeed. Yeah, it just shows the difference. Thanks for pointing that out, Ted.
Yep. Yeah, but internally, the SDR produces a DC output at that 0 Doppler shift. And I think that must be some minor quirk with the ADC, analog to digital conversion. Anyway,
It's actually kind of a function of it's the power at 0 hertz in Doppler, and it pretty much comes out of the FFT software. Somebody else?
Well, actually, it goes into the FFT software and comes out.
Well, I happen to have one of these as well, and it seems to be a design feature or bug of this particular model, because I have a different model of Smart Key that's not the XR that performs more like the RTL SDR, as far as it doesn't have that the same problem with that DC offset. And I think somebody was telling me that it has to do with the way that the up and down conversion on the front end works before it gets digitized. Anyway, I think it's an inherent design feature of that particular model versus the other one. So I actually found that a different model was a little bit easier to work with because it didn't have. I found that it was really difficult to deal with that DC spike. I mean, you can kind of brute force it after the fact, and do post processing, but if you don't have to deal with it at all, it's kind of easier.
If I could make a point, actually, that DC spike is due to the fact that the local oscillator and the signal that you're looking at, when they're matched, you have 0 IF output. So you're actually seeing power from the local oscillator coming through. That's what's called a DC spike. If you have a second superheterodyne stage where you actually shift that, then you don't see that because you always have an IF that's not equal to 0. I don't know if that makes any sense or not, but
Yeah, so basically single conversions have that problem and double conversions don't.
correct. And exactly. And so the RTL SDR is essentially a single conversion, and some of the other receivers that do have a double conversion do not exhibit that because you always have a non-zero frequency IF. So you're always offsetting the local oscillator that bleeds through the mixer. So, for example, the air spy is a double conversion, and I don't think the air spy has that central spike, if I'm not mistaken.
Okay. All right. Thank you very much. Any other final questions?
John, what are you writing all this cool software in?
Java.
I want to find out more from you eventually. Figure out when's a good time to, where it's stable, maybe. Let's talk some more. Thanks.
I think Francesco.
Well, I've been doing Java programming for 30 years now.
Yeah. I think
not as
And it looks
professional.
that way.
Did you have a question,
Great
Francesco?
results.
Do you have a question, Francesco?
I want to ask you to John if he ever heard about the Virgo software.
Virgo? No.
Yeah.
I haven't.
Is
Is this the Despera stuff that you're talking about?
No, it's a
DSPIRA.
collecting software that has some nice plotting results. It's
Yes.
pretty nice.
I have never tried, but I only heard about it. And it's considered somewhat professional or semi-professional software.
No,
It's
no, I
free.
haven't. I think I've got past, the point of selecting in my acquisition software. I'm perfectly happy with what I have at the moment. And if I'm going to spend time, I need to spend it on the next stages, as I say. Yeah.
Okay, thank you. Thank you.
All right, then. I'll unshare my screen.
Okay, thank you very much, John. So,
Yeah, pleasure.
I pass you back. Sorry, pass back to Jason now. Thank you. Thanks, Jason, for letting John talk there.
Oh yeah, that worked out good anyway because I ended up having to do an antenna checkout real quick. So, so I'm going to go ahead and share my screen again, and select that. Okay, there we go. And then I'm going to put this in presentation mode, and I think that. All right. So can everybody see it?
Yes, indeed.
All right, so now my second presentation is essentially talking about doing hydrogen line detection of nearby galaxies with my smaller dish, and I go through kind of the details of the process. But this this process will work with any size dish as long as it's large enough to get enough signal to noise ratio to actually detect anything as far as these smaller signals are. But let's get right into it. So I'm going to start out with a brief introduction to hydrogen line and galaxy spectra. So this is probably old news for most here, but I kind of wanted to tailor this to complete newbies as well. So I kind of wanted to go through what is the hydrogen line in general. And so hydrogen line is an emission line caused by the ground state electron of neutral hydrogen changing spin states. And so it changes from being aligned with the nucleus to anti-aligned with the nucleus, and the difference in energy between those two states is very, very small, and corresponds to electromagnetic wavelengths of 21 centimeters. The hydrogen line was first observed in 1951 by Harold Ewan under the direction of his PhD supervisor or PhD advisor, Edward Purcell at Harvard University. And he was using the horn antenna that's shown here. And oh, by the way, Andrew, when you get to Green Bank, this is actually at Green Bank now. They moved it from Harvard Observatory to Green Bank, and it's permanently on display there. So you will actually get to touch this when you get there.
Well, you've just
and it's
signed.
Not a replica.
Yeah, you've just
it's
signed
the
yourself
real
up
one.
to take a picture of me with it, so I can use that in my talks in the future.
Absolutely. So yeah, that is one of the cool things about going to Green Bank. There's some pretty neat historical artifacts on display there. This is a map of the Milky Way. It was the first structural map made of the Milky Way, and it was using the Doppler information from observing the hydrogen line. So Jan Oort, of Oort cloud fame, was the one that did this. One thing you'll notice, so just to orient ourselves here, the solar system is right here at this spot, off-centered, and the center of the galaxy is then in the center of the plot here. And what you notice, there is an artifact here where there are these blind spots at narrow angles towards and away from the center of the galaxy. And those are due to geometry. They're artifacts of the process of the trigonometric methods that they use to convert the Doppler information into spatial information. And what happens is, as you get close to the line of sight with the core or the edge of the galaxy, the rotational motion of the gas around the center of the galaxy becomes entirely tangential to our point of view, and so there is no Doppler shift. And so without Doppler shift, you get no spatial information. So you detect plenty of hydrogen, you just don't get any information about the location because there's no Doppler shift. So when you're observing external galaxies, such as M31 or M33 or some of the other nearby spiral galaxies, what you see is, instead of a complex of, a single peak with some smaller peaks, because of like what we see in the Milky Way, due to, signals coming from different spiral arms, what we see is something that looks like Batman. So we see these two peaks with a flat in the center, and I'll show that in the next slide. But what happens is the single peak from the hydrogen emissions from the galaxy gets split into two because of the rotational motion of the galaxy, and so you get a blue shifted peak and a red shifted peak, and a lot of times that's overlaid upon an overall blue or red shift of the entire galaxy from our perspective. And the distance between the peaks indicates the orientation of the galaxy from our perspective. So if we're seeing it more edge on, the separation is more pronounced. And if we're seeing it more flat or face on, the peaks get really close together. In fact, if it's perfectly face on, the peaks are directly on top of each other and they become one peak. Because again, all of the motion is tangential to us and there's no Doppler shift. This is an actual real-life example of this, showing the photo of the galaxy and showing its orientation, and then scaling the hydrogen spectra of these galaxies so that their horizontal scales match. And so what you can see here is the hydrogen spectrum of M31 is very wide because M31 is very edge on. M33 is a little less wide because it's a little less edge on, and so forth. And when we get to something like M74, it's almost face on, and so you see there's barely two peaks. It's almost just a single peak. So my mini dish setup is described here. So I got again, this was what I showed in my build presentation previously, but this is just showing the parameters or the specs of my setup. So I got a slightly larger than 1.5 meter diameter and a focal ratio of 0.35. Half power beam width is 11.5 degrees. My reflector is aluminum window screening. I have a simple tripod base, no tracking, no equatorial mounts or anything like that. And I believe that this is the smallest aperture attempt at detecting galaxies outside of the Milky Way. As far as I can tell, nobody's done it with a smaller aperture yet. So, and I think we're pushing the limit here. I think this is getting to the limits of how small of an aperture can actually detect these two galaxies.
Jason, what's in the background in the bottom right?
Oh yeah. So this dish is very small. It's very portable, and I actually brought it and demonstrated it at the open house, the spring open house at the VLA, which is where I work. A very large array. And over here in the upper right of this photo is actually the prototype next-gen VLA dish. So that's the new one. And we've just actually started collecting data with that. We had first light on that about a month ago, I think. So that's kind of exciting. So it's kind of a neat little picture because I got my little mini dish here, and then in the background you got this prototype next-gen VLA dish in the background there. So yeah, thanks for prompting me on that. I almost forgot about that. So my front end is a cake pan loop feed. It's based on Alex Pettit's design, and I do give the URL of that in my references at the end of this. So if anybody's interested in the detailed specs for this, I do reference it at the end. I use the Newelec Sawbird H1 for my LNA and bandpass filter. And then my receiver signal chain is an AirSpy Mini mounted on a heat sink for stability. And I have that inside the house. So I have my 25-foot cable running up to the window, and then I have my receiver actually on my desk just inside the window. And then I have my laptop and my my SDR both sitting on the table or on the desk there. And I use SDR Sharp with the IF averaging plugin as my data collection. And so then once I have my hardware set up, then I'm going to describe my observing planning. So I make an observation plan by gathering information from credible sources. Usually I just go online, type in the search engine the designation of the galaxy, so I can find the astronomical coordinates for it, and also to get an idea of what the average radial velocity should be. And also I look up, it's helpful to look up hydrogen spectra from professional surveys so that you have something to compare your results against, which kind of lets you know what you're looking for and in what part of the spectrum, right? So once I've gained my observation data, the data about the target, then I have to find the local of standard of rest value to correct the measured Doppler velocities for the orbital motion of the Earth. And I use a page hosted by Green Bank Observatory, and I also give the URL for this at the end in my references. But I just type in the date and the RA and DEC coordinates. I don't worry about the time because I'm sighting on the meridian anyway, so any rotational components would be 0 anyway. And this is optimized for the specific location of Green Bank, and I'm obviously not at Green Bank. So all I care about is the orbital motion part. So I type in the date, my right accession declination, and then it tells me what the VLSR correction is. And in my observation plan, in my notebook, I write down that value, as well as my my coordinates and how those translate to as and L in my location. I also put down my center velocity that I want, and I got that from the spectral profile and the other information here. Minus 180 is about what I'm looking for M33. Then I use Stellarium as a convenient tool for estimating my transit times for my observation. And so what I'll do is, since I know the half-hour beam width of my dish, I go into my Stellarium app on my phone, and I zoom in until my field of view matches my half-hour beam width. And then I center I set my field of view to where it's pointing at either south meridian or north meridian, depending on, you know, which makes sense for whichever observation. In this case, it's south, so I face it at an azimuth of 180, and then I set my declination of my field of view so that the object will pass through my screen, and then I set my date and I increment the clock until I find when the object I'm trying to look at just enters and exits my field of view, and I write down those times, and then that tells me what my main transit times are, my start and stop times. And then what I do is I find the duration of that main transit, and I divide that number by 2, and I subtract that half transit value from the start time to find out when I should start my pre-transit data collection. And then I also add half that amount to the end, and I collect data that much after the post-transit, so that I can use pre- and post-transit data as my reference to flatten my background. And this works really, really well, actually. I've been doing this for a while, and it does a great job of flattening the background and suppressing a lot of the local Milky Way signal. I also calculate the desired center frequency using the non-relativistic Doppler approximation formula, which I give here. And I actually created an observation planning tool that I believe I've also allowed Andrew to put up on his site. So if anybody wants to use that, I think it's available. If not, let me know and I'll send you a copy. But basically, I have it set up so I can type in the center velocity I want, the VLSR correction, and then it'll tell me what center frequency to set my my SDR to for my observation. But this is the formula if you want to do it by hand. So then I collect the observation data. So I used Polaris as my guide at night, and I laid out sighting stones in my yard to mark the meridian. And then that allows me to then align the azimuth setting of my dish very easily. I have a piece of plywood with a center line marked on it, and I set it between the 2 stones in the middle of this line here, and I just line it up, and it's dead on, or well, as close as I can get by eyeball anyway. And with this method I did do, when I did my sun scan of my new dish, I was literally off by 6 minutes, which is less than 2 degrees. And I was able to tweak it just a little bit based on that information and get it probably dead on, or less than a quarter of a degree off, I would say. But plus or minus 1 degree is enough for this type of drift scanning anyway. So then I shim my tripod with books or plywood or whatever to to set the elevation to what I need for the observation I'm doing, and then I tie it down with bricks and paving stones to keep the wind from blowing it over. And then I set the center frequency to whatever I calculated in that previous step. And here are my actual IF averaging settings that I use. So I use an FFT resolution of 512. And I set, you can see kind of my other settings. I adjust the gain and level to as I want to just, all that really does is makes the display show the real-time spectrum in the center of the screen. It doesn't really affect the data collection at all. And then I make sure I set the path where I want it to save my data files, and I set my default file name. And then what it does is, as it collects files, it'll just append a 3-digit index number to that file name for each file. So it'll be like, you know, that file name -001, 002, and so on. I always start collecting my data at least an hour before my pre-transit start time, so that the system has a chance to stabilize before I collect any meaningful data. Because it does take, you know, 15 or 20 minutes at least for it to really stabilize. Once I'm done collecting my data, then my data analysis process starts. And so what I do is I look through my data collection files that IF averaging has collected for me, and I look at the timestamps on those files, and I match them up with my pre-main and post-transit start and stop times. And so then I can find out, okay, which files do I need? And the great thing is Ted Klein has built a utility in his in his Ezra suite called IF. It's called EasyCol IF Average, and what it'll do is it'll take all those IF averaging files, pull them into a single file that's in the format that the EasyCol utility collects, and then so it makes it one step then to take all of that data and dump it into. In my case, I do my analysis in Excel, and so I can just collect all of that stuff, dump it into Excel, and then do a transpose operation when I paste it, so it swaps the rows and columns, and then it's set up for my analysis tool to work on it. So it makes it really easy. It takes 2 steps in about 5 minutes rather than 20 or 30 minutes worth of tedious copy and pasting like I had to do before. So I really appreciate that, Ted. In my analysis spreadsheet, once I copy those data file columns in, now what I end up with when I copy in the stuff from the EasyCol conversion, I end up with a bunch of columns of amplitude values, but I don't have the frequency values because it doesn't generate that. But the header in that file contains the start and stop frequency. So then what I do is I just type in the start frequency, and then in the subsequent cell, then I take that, I point to that previous value, and I divide it by my bandwidth times, you know, or I multiply times. I'm sorry, I add a value that's the bandwidth divided by the number of buckets. And so in this case, it's 6 megahertz divided by 512. And then that generates all those frequencies for me. Of course, double check to make sure you did your math right, and make sure the final frequency value matches what it's supposed to. But then what I have set up then is that when you type in the VLSR correction at the top of the sheet, it automatically generates the corrected velocities for you. And then once I've got that, then I'm able to, and this shows the math that I use for that. And what I do is each subsequent day, I just copy this sheet, rename the tab with the next day's date, and then copy the new data in, but I leave that right column alone, and then it automatically then calculates those corrected velocities for me. Then what I do is in the analysis sheet, I pull in the average of the pre and post transit data, and I put that in the reference column. And then I take the average of all the main transit data, put that in the main transit column, and then I copy all those down the columns. And now what I have is when I go to the raw spectrum, I take the main transit, divide by the reference, which is the pre and post transit data. I take the log 10 of that, and I multiply times 20 because all these values are basically linear amplitudes. And it generates a normalized dB value for me. Then what I do is in the actual spectrum column, I do just a running average over, I can't remember how many cells I do the running average on. Oh, a 9-point running average. And that seems to smooth it out pretty well without throwing away a bunch of useful, data. These are what the raw plots look like once you've done all of that. This little blip you see right at 0. So the horizontal scale is in kilometers per second corrected Doppler velocity, and that blip you see is right at 0, and that means my VLSR correction the math was right. If your math is wrong, if you get your sign wrong, that won't be at 0. It'll be somewhere like plus or minus of that. And so that's always a good check that you got your correction right. So it should be at 0. The next step is then to go to the flattening tab, where I can do some post-processing to correct the residual background slope. Now, as you can see, the raw spectrum is pretty flat. It's pretty decent, but when you zoom into the small, tiny vertical scale that we're looking at for these external galaxies, the slope becomes pretty significant, even with all that correction. And so I have up to a second-order polynomial fit that I can use then to correct the background. And so in this case, what I did is I zoomed into just the area where I knew that the M33 spectrum should be, and I look at the portion just to the left of that where it should be background, and I kind of set my background correction to that. And once I've done that, then I should have a normalized and corrected spectrum. This is a result of this process with 8 days of data collection on M31. And then this is the result of 12 days of data collection on M33. And you can see the reference profile from a professional survey to kind of compare against. Now this really pronounced vertical line is that residual Milky Way blip that we're butting up against. And it's impossible to totally get rid of that because it's hundreds of times bigger than those external galaxies. So even though our background correction is suppressing it quite a bit, it doesn't suppress it entirely. So you're always going to see that close to 0 or around that range. So and then here's my references. So I will be making a copy of this available to everybody. I think I can. I'm not sure I can attach it to the chat, but I'll send it to Andrew and he'll put it up on his site. So if anybody wants to copy this, all of my reference links are here. So the one that's really helpful is this Green Bank velocity correction site. And then there's also the detailed build and engineering specs for that loop feed that Alex Pettit designed, and it works great. It's such a simple build, and it performs so well. So I highly recommend it. So that's all I got for my presentation. So I guess I'll leave it open to any questions now.
Well, thank you very much, Jason, for two fantastic talks. Absolutely wonderful. I think you've probably blown everyone's mind with what you've achieved there. And each time I hear these talks, I mean, they're great to start with, they get even better every time. So, wow, I suspect there'll be even more great stuff by the time we get to the Eastern Conference in a couple of weeks. So who would like to start the questioning? There must be loads of people who've got things they'd like to ask or comments they'd like to make.
Jason, to complete the video record, which external galaxies are you suggesting we start with? What's the list?
So even though M31 is definitely the largest signal, I would suggest people start with M33. It's about half the size of M31 signal, but it's also much narrower band. It's a much narrower spectrum, and so it's easier to flatten the background, especially if you're using an RTL SDR or a Smart T, because your bandwidth is limited to less than 2.4 megahertz, and it's really difficult to deal with that on M31 because it's so wide. The spectrum is enormously wide. Now, it's easier if you have an AirSpy Mini where you have a nice 6 megahertz bandwidth and a pretty flat passband. But M33, I would suggest that's where people should start. And I would also suggest, if you haven't tried it before, don't start with a 1.5 meter dish. Start with something at least 2 meters or bigger. Probably 3 meters would be, something close to 3 meters would probably be the best way to start. But if you have a 2.5 or 2.1, definitely try it. I mean, it might take several days worth of data collection, but you should be able to see something with M33. Now, as far as going to anything past M31 and M33, the next one down the list would be M101. And I think anything smaller than a 3 meter dish, you'd be pushing it to see that. I'm hoping once I get my new dish extended to 3.3 meters, I'm hoping to be able to go after a few more. There's also another one, actually, that what's his name? Edward Mole has suggested, and that's actually IC342. So my suggested list would be in this order. It would be M33, and then M31, and then IC342, and then after that you could try for M101. But like I said, anything smaller than 3 meters, M101 would probably be pushing the limit. Yeah. But if you have something larger than 3 meters, then after you get those done, there's a handful of others that might possibly be in reach. And as I start messing with my bigger dish, I'll keep everybody posted on those as well. It's possible, I think, maybe M81, M74, NGC 2403, and Holmberg 2 might be ones that would be possible to detect. So, but I'd say the low-hanging fruit is M33 to start with, though. So, All right. Well, thanks, guys. I'll stop sharing now, and like I said, I'll make this. I'll make both of these presentations available to everybody, probably through Andrew. I'll probably email them to Andrew, and then he can upload them to his site. So.
Brilliant. Well, that'll be fantastic. Thank you, Jason.
Yep.
Oh, and thank you very much again for giving us so much of your time tonight and giving such excellent presentations.
And also, if anybody wants to try their hand at designing and building one of these portable dishes, definitely reach out, and I'll pass along anything that I can to help you out. I think they're definitely an accessible build project for do-it-yourselfers. I think the most difficult part is probably cutting out the ribs, but if you know somebody that has a really nice bandsaw or a scroll saw, you could probably get that part done. Or possibly if you know somebody that's got like a a laser CNC cutter or something, that might be a way to do it. But my thought was to try to keep it as low tech as possible. So.
Okay. Well, for anybody that missed your references, I've just added them to my website there, astronomy.me.uk. So that'll be the latest post for anybody that wants to look at it.
Is Jason's email there also? I would definitely like to follow up on this.
I think probably the best thing is if you contact me, I can then pass you on to Jason.
Yeah, I can type my email into the chat here. So
if you put it in the chat, it will appear on the video, Jason.
Okay. Yeah, that's fine.
It's up to you if you're happy with that.
Yeah, it's okay.
Okay, so it'll be in the chat. Okay, brilliant. Well, thank you very much again. Brilliant. Well, let's give everybody else a chance to talk if they'd like to. So I'm not sure who we've got left at the moment. Most people by the looks of it. Fantastic. So, Bob, is there anything you would like to talk about tonight? So, Bob Hamers, let's start with.
Yeah, I can give an update. Let's see, how do I share my screen here?
It's next to leave at the top right-hand corner.
Yeah, it's still this security thing.
What security thing is that?
Let me just see here. I try to share content. Okay, here we go.
And then you get a choice of either sharing your entire screen, which is generally easier because whatever you have on your screen will appear, or you can choose a window which is more secure in the sense that you don't accidentally show something you don't want to secure, but it often means you end up showing the wrong window, especially if you change between windows.
Yeah, it's wanting me to. Why don't you go on to somebody else first? I have some stuff I could show if I can get this security thing settled.
Jason, there's a question for you in the chat.
Oh, yeah, okay.
So what to say, Jason, do you think you'll ever be able to detect any of the satellite galaxies in the Milky Way with your radio telescopes? That's from Richard.
Yeah, I'm assuming you're referring to the Magellanic Clouds. Is that correct? Yeah, so I think so. As far as I understand, they're really only visible from the southern hemisphere, but I would think that they should be probably brighter hydrogen sources than even M31. So that'd be an interesting collaboration with our Australian counterparts. If one of them has a small, like 2.5 or 3 meter dish, I bet they could go after those. Now the trick may be that their radial velocities are fairly small, so it might be problematic to separate them from the Milky Way signal itself if they are, close to zero radial velocity. But that would be an interesting, project.
So they're far away from the galactic plane, so we could find them as spots, but I'm not sure they have much rotation about their own centers. So you may not see peaks. You may have one big bump.
Yeah, it's not so much the rotation. the problem is, even if they're well out of the planes, if they're really small signals compared to because the ever-present signal, even completely perpendicular to the galactic plane, is huge compared to a lot of these extragalactic sources. And I'm not sure how large the signals from the Magellanic Clouds are. It'd be interesting to look that up. I think I'd like to go do some research on to see if anybody's done some, see what the professional hydrogen surveys look like for those, because that would definitely be a guide in how to get started with that. So that's where I started when I started going after M31 and M33. Was I went straight to the professional surveys to see what they had to say.
So there's a Planck movie showing different velocities, and the Magellanic Clouds show up way at the end, meaning they're not a zero velocity from our location. So it's fun to see them off to the side.
Yeah, well, that's a good thing then, because that means that they're clear enough of the local signal that's close to zero that we should be able to separate them easily then.
Yeah, so there's hope. You could find that, but I think it would be one big bump way off to the left or the right.
Oh,
Fun.
yeah.
Thanks.
Yeah. Cool.
Okay.
Yeah, that would be a fun project to undertake, I think, so.
Okay, thank you very much there, guys. Okay, it looks like you're in action now, Bob. Is that right?
Yeah, can you hear me okay?
Indeed we can, and we can see your presentation as well. So you have the floor.
Okay. So I've been basically working with a relatively simple horn antenna that I've built. I built it a few months ago. It's made from lightweight corrugated polyethylene panels and aluminum foil on the inside, and essentially a waveguide down here for the collection. There's a couple more pictures of it. It works pretty well. I mean, here's a real-time hydrogen signal that I was getting using this setup. I started off using an AirSpy R2, but I had a bunch of problems with it with a spur that was showing up right at 1420 megahertz, and it was really hard to get rid of. So I switched over to a different radio, and I'll just show that in a minute. So I've been using the SDR Play RSB2 and using a new radio that I slightly modified from one that I pulled off the web from the DSPIRA project. And this is basically working quite well, within the limitations of what you can do with a horn. So I've been trying to make two-dimensional maps. So I did a series of measurements over 2 weeks where I recorded spectra every 3.5 minutes for more than 24 hours each one. And I did that with my radio horn pointed along the South Meridian at 9 different elevations that were each 10 degrees apart. So that gave me about 4,000 spectra, each at a different right angle or right ascension and declination. I did calibration spectra at the beginning and end of each 24-hour period, mainly by shifting the frequency over to about 12. Instead of 1.42, I centered it at 1.418. So basically just moving out of the hydrogen region so that I had a clean pass band. And then I've done, I've written my own software, so I have a lot of experience with data analysis and coding for analysis. And so I'll show a little bit of that in just a minute. But I've basically written in Python and largely using the standard Python packages along with the AstroPy, which is somewhat specific to make things work. So one of the big things I ran into is most of the time I get good spectra without very much RFI, but every once in a while I do get some radio frequent interference. And here's that 1.42 gigahertz spur that I was getting with the AirSpy R2 that I could never get rid of, no matter what I did. It's not the zero, it's not the zero spike that you often get. It doesn't shift when I shift the passband or anything. It's just always there. And it went away when I went off to the other one. But one of the things I focused on early on was getting the new radio software set up, and in particular, getting the largest number of points to do the FFT, because I learned that if you have, I'm doing 4,096 points per FFT, and at that point, it becomes very easy to use a simple median filter to get rid of the RFI, almost including this big spur, which is at orders of magnitude bigger than my actual signal. And I'll just contrast that with, somebody had mentioned the Virgo software before. Ayush Tripathi, who's active on the SDIR, or on the SARA chat list, had recommended I try a package he's been working called H-Line that couples into the Virgo software that someone else mentioned. And this, I think, only does maybe 1024 points per FFT. So over the same spectral range, the points are farther apart. And because of that, it's somewhat harder to do the median filtering to get rid of the spikes. And so this is about the worst case that I'm just showing here, but you can see the median filter does a reasonably good job of getting rid of that. Let's see. I won't talk too much about this if anybody has questions about it. But what I did then was take these 4,000 spectra, calibrated each one of them, did a curve fit to get rid of the sloping background, and then integrated to get the total hydrogen emission spectrum, and essentially plotted the area under that hydrogen emission versus the RA and DEC of these 4,000 spectra. So there's a routine in the matplotlib library for Python where you can give it a scatter plot of intensities, or in this case area under the hydrogen emission curve, measured at different values of RA and DEC, and it will essentially interpolate to make that into a nice two-dimensional plot. So I was pretty happy with this. You can clearly see the two bands of the Milky Way as it cuts through twice per day. So I was interested in trying to take this one level further, and that normally this is presented as the right essential and declination, but if you translate that into the galactic coordinates, then you can get a different kind of plot like this. So this is using Python to essentially do the same thing, except that instead of plotting the data as a function of the right angle and the declination, now plotting it in terms of the galactic longitude and galactic latitude. And that coordinate transformation is pretty easy to do in Python. And so kind of the interesting thing about this is that it clearly shows that the hydrogen emission is in fact confined to a plane. Right? It's a very narrow plane centered about 0 degrees galactic latitude, and as a function of longitude. I can't quite get to the galactic center, at least from my location in the northern hemisphere back in May. This was not above the horizon, and there's some regions of the coordinates where I just can't access from the northern hemisphere. But I was pretty happy that this means like my coordinate transformations are all working properly, and I can plot the data that way. And then more recently, I've been going back and looking at some of the individual spectra. So this is just an individual smattering of spectra measured at 0 degrees galactic latitude. So I'm looking in the plane, and then as a function of the orientation within the galactic plane. And you can nicely see that there's here's the hydrogen from our local vicinity, but you can begin to see other peaks that are coming from the various arms of the Milky Way. So this one's probably coming from the Perseus arm. If we just draw a line out from, Jason showed this, the idea of the galactic coordinate system before, but 0 degrees corresponds to looking toward the galactic center. Looking out here, we're at 100 degrees would correspond to spectrum right about here, and you can see there's 2 well-defined peaks in addition to the local hydrogen. And so what I've been trying to do now is work on trying to really understand how to identify when we have these different essentially cuts through the arms of the Milky Way. How do we actually map those onto the spectra that I'm seeing, or really the reverse, right? How do I take these spectra and know that this is the Perseus arm and that this is the outer arm and not the reverse? Because of the complicated geometry, it's not an exactly simple coordinate transformation.
Before you leave the slide, what is the N like November? N plus O, it says.
What is N? N is let's see. Well, it would be Norma arm, I guess. Actually, that's probably a
It could be a different name for the outer arm. Many different people have different names.
Yeah, recently there was a paper that basically argued that the Norma arm and the outer arm should be combined. So this is the Norma plus outer arm. That was by designation anyway. So,
thank you. Great.
Yeah, so that's what I've been working on. I also was trying to, this is about 1 meter in size. I was trying to build a 2-meter dish antenna from aluminum and utterly failed. So I'm kind of back to the drawing board on that, but I was really intrigued by Jason's talk, and maybe that's what I'll be doing next. Yeah, I'll just mention this mapping from the spectra onto the onto the Milky Way itself is pretty complicated because you've got to worry about the geometric factor of what is the velocity along the line of sight, and the fact that the velocities are faster out here, but they may be cutting through at smaller angles, makes it not so simple. So the best reference I found was actually this one little figure from a recent paper in the Astrophysical Journal that mapped the local velocity as a function of the galactic longitude onto the different arms of the Milky Way. So it's the paper itself is kind of hard to read, but this figure I found extremely useful in trying to interpret what I was seeing. Okay, that's it from me.
Wonderful. Thank you very much indeed. Has anybody got any other questions they would like to ask about that presentation?
Bob, that's great. That's much fun. You're going seeing so many interesting things.
Yeah.
This is Python you're playing with?
Yes.
Magnificent.
Yeah, the Python with the AstroPy software in particular, I mean, the calibration is pretty much just basic Python with the NumPy package and matplotlib for doing the plotting, making the 2D plots, and then the AstroPy software package has a lot of really nice add-ons for doing coordinate transformations, and that turned out to be, the coordinate transformations are pretty non-trivial, but it does a nice job.
Okay. Anybody else? Okay, well, thank you very much, Bob. That was quite brilliant. Thank you very much. So, Bob Oleska, is he still on? Would you like to, if Bob's still here, would you like to say anything? Have we still got him or not? Or has he gone? I think he might actually have gone looking at the list. Okay. Okay, we've got Ted's put something into the chat there about easy radio astronomy for anybody who's interested. Okay, Francesco, would you like to anything you'd like to talk about?
My conclusion is with so simple instrument, handmade instrument at home, you can achieve such results. It's for me, it's incredible. It's astounding.
That's one of the reasons that we have these meetings, just to show that to people, show what can be done. And I remember years ago with a friend, we used to do a lot of visual observing, and we started with very large scopes, very expensive scopes, and then over a couple of years we got to smaller and smaller scopes and cheaper eyepieces, and lo and behold we could still pick up smaller and smaller galaxies and sort of light, fainter and fainter nebulae. It is amazing what you can achieve once you know how. So yeah. But how about yourself? Have you got anything to present about what you've been doing with your own kit?
At the moment, is I'm working through a software to integrate ESRA with other SDR receiver. I am interested to use my AirSpy with ESRA, and with the aid of AI, Claude, for instance, is I'm running ESRA with my AirSpy Air 2. I want to write some parser to collect data from other observatories. For example, I've just made a parser for SALSA radio telescope data to import directly in ESRA, and I plan to made the same with other observatories, for example, Effelsberg in Germany or Green Bank in USA. But at the moment I'm in very early stages.
Okay.
I'd like to help if I can. With Ezra, my concept was convert it all to a very simple database, format at least, with these translator programs. They act a lot like a collector, and so I call them easy call and then some characters after that. Let me know if I can help. I may have one for Green Bank already, for example.
Oh, thank you. I discovered that I was convinced that ESRA was limited to 156 channels, but I discovered that there is no limits. This is not the limit. I
haven't found the limit anyway. Yeah, there's a parameter to change that. I start off with the defaults being simple. Please continue.
I discovered that I used 4,096 samples from the Effelsberg telescope. It was a sample survey, and I used with this resolution.
Very good. Let me know if I can help with translators, though. I'm practiced at it now.
Okay. Thank you, Dad. Excellent.
Okay. Well, thank you very much, Francesco. Thank you. Okay. Richard, is there anything you'd like to talk about? I'm trying to remember whether Richard has access to audio. I don't think he does. Oh no, he's already said. I can see his message. Very little to report here. Still building my radio telescope. Okay, I've seen that, Richard. Thank you very much. Right. So, Royston. Have we still got Royston online? Yes, apparently we do. Royston, are you still there? No? Okay. Okay. Right. Mark, how are you getting on? Have you managed to progress at all with trying to deal with your RFI problem?
Sorry, I haven't got much to add concerning the hydrogen line. I've been messing around with my, what do you call it? My solar radio antenna. I managed yesterday to destroy my linear regulator.
How did you do that?
I connected pin 1 to pin 3. So for people who know the LM7805, anyhow, it destroyed it. So I've ordered some more. But what I've been using Grok as a kind of advisor how to build this system, and I know I'm deviating from the hydrogen line, but what Grok is saying that you should separate the analog from the digital side to reduce a spillover of noise, and I've discovered you can use this USB isolator. So I will have the VLF receiver and the sound card in a separate box from all the other stuff, from the Pi Zero, and to transmit the data from the VLF receiver and the sound card. It'll go via this USB isolator. I didn't know such things existed. ADUM 3160. Apparently it's a standard device. If you've got a signal and you want to separate noise over USB, you can use this digital isolator. I don't know if anyone's familiar with these.
Have you tried using it yet? Or is that something
No.
that you're doing? Well, please do come and tell us about how you get on with that.
It's quite incredible what there is on the market these days. It uses air core transformer technology, and it's in a chip. So that's what I'm doing at the moment, trying to stop destroying linear regulators.
Right. But, well, how you get on with that, I think, will be useful to this group as well as the VLF group. I think everyone would like to know whether that works or not.
Yeah.
Yeah. I mean, for anybody that doesn't know, poor Mark here has had absolutely awful problems with radio frequency interference.
Yes.
Destroying all of his different radio astronomy projects, but he still persists, which is very impressive. I'm sure he'll get there one day, and the lessons he'll learn will be of use to the rest of us.
I must admit, this evening it was fascinating, which is why I'm still here. Bit over my head, some of that stuff.
Well, what I'd say, if England can win the game last night against Mexico, you can succeed with RFI. just need a few good substitutes and you'll be there.
Yeah.
Okay.
Thanks, everyone.
Brilliant. Thank you very much, Mark. Now, Richard has put a question to everybody in the chat, which says, professional radio astronomers are having issues with mega constellations in orbit. Have those in the amateur community experienced this as well? And if so, are there mitigation strategies? Is that something that's affected anyone's hydrogen line observing here, these satellites? Or would they expect it to affect their hydrogen line observing these mega constellation of satellites? My immediate guess would be that they're transmitting on a different frequency, which is not relevant to us. Would that be right, Adrian?
Yes, that's, well, as we all probably know, the 1420 hydrogen line is an international protected frequency for every country. Of course, anyone that adheres to the international laws. So, yeah, there's not any intentional transmission in that frequency. However, not all transmitters are perfect, and they have harmonics and spurs and whatnot, so there could be some bleed over. I think a lot of the interference is probably in other frequencies, as you try to suggest there, which are not protected, and so that could be a problem. I have seen some interference in some raster scans that I've done for the frequencies more closer to the hydroxyl maser emission lines around 1660 some odd megahertz or 1612, and those are pretty close to some frequencies used by Inmarsat and some of the other constellations. So yeah, if you're looking at other observations besides the hydrogen line, then that might be a problem.
Yeah, I think that mobile phones cell towers can be a problem, can't they? Because they're very close. I think certainly in the UK they're close to the 21 centimetre line. I mean, they're outside of it, but obviously quite strong signals, and they can bleed over and produce harmonics. That's what I understood.
Yeah, cell frequencies bracket the hydrogen line area below and above it also. So yeah, that can be a problem. The so-called front end overloading can be something if you're very close to a radio telephone tower. Just the extreme power of the emissions can drive the front end amplifiers to nonlinear saturation, and then that reduces the overall sensitivity of your receiver, and then it can introduce other harmonics and spurs inside your receiver due to other types of mixing that go on with the way the system works with the local oscillator and so forth. So that can be a problem. Doesn't have to be on frequency for you to necessarily get the RFI. Some of the presentations today have shown some of those results, the spurs and whatnot that people see surrounding the hydrogen line observations. So yeah, it can definitely be a problem, not just necessarily from the satellite transmissions, but the local ground. I myself experience a lot of radio frequency interference where I live. I'm in San Diego, California, and very close to a military air base, the Miramar Marine Corps Air Base, which has a huge amount of military traffic. They transit over my home. If I would point my antenna to the south, for example, to try to do observations, that's right in the flight path of some of the military aircraft that would just fly right straight through that beam pattern of the antenna. And those things are just incredible, all the frequencies and harmonics and God knows what else they're using in terms of radio frequency interference. So it doesn't just have to be necessarily satellites. A lot of ground interference, like I said, if you're close to any military base, they use all sorts of frequencies, some assigned and some not. That can be a problem. So yeah, it's definitely a problem that mitigating can be quite a headache. So yeah, good luck.
Okay, Richard's asked another question, which is, was there a plan for a Russian constellation of satellites that used a frequency near 21 centimetres? So the information I can find is that there have been persistent reports over the years of a proposed Russian satellite system that would use a frequency close to that, but nothing that's ever been officially announced or actually launched. And as yet, the 1,400 to 1,427 megahertz remains internationally protected. Although I know that the Chinese produce radios, certainly at least small handheld radios, that will use that frequency, because I've got one. But there is a Soviet or Russian GLONASS constellation, which I think is the one that you were mentioning there, Adrian, that uses 1602 to 1616 megahertz, which, as you say, is close to the protected 1612 megahertz hydroxyl maser astronomy band. So which caused major interference, particularly in the 1980s and 1990s, until they made changes. So that's the information I can find, but I don't know if anybody's got anything they want to add to that one, Richard's question. Okay, no. Adrian, is there anything else that you would like to talk about today?
No, I'm extremely pleased with the presentations done today. They've certainly a lot of food for thought. Thanks to Jason for his really marvelous antenna construction presentations. They're really excellent, and the other presenters that have provided some of their data. So really appreciate all the hard work that they've done. So yeah, just really fantastic meeting tonight. And thank you, Andrew, for hosting this.
Oh, it's been a brilliant meeting. Really great. Okay, moving on to, have we still got Ted Parton here? I think he's gone, but just to double check the list. All right, no, he's left. Okay. Steve has left as well. So that leaves us with, how about Andrew? Or he's left as well. So we've got left that hasn't spoken. I think Ted, I think you might be the last one.
It's been fun. All kinds of cool creativity going on. This is great. Jason, let's see. On Ezra, it'd be great if I could just plot all those frequency spectra, but they're so weird. They're away from the Milky Way frequency of 1420. And so I've had to make changes. The changes are slowly coming so that I can have different spectra with different frequency endpoints integrated on top of each other. That was the hard part. And so I'm making progress on that. So there's hope there as well. And then I thought it'd be fun to have Ezra also do integration from with intensity or maybe power versus the x-axis of right ascension. I can do that for a couple of data files, but after that it just gets too unwieldy. I should do the integration, or at least the summation, as I progress, and then I can take as many data files as you want to wait for. But I have to rearrange the program to make that happen. So I think that would be kind of fun. Integration, not just in time, but or on a daily axis, but also on right ascension or maybe galactic longitude. So ideas for Ezra keep popping up. Thanks.
Brilliant, thank you. I've actually sent you a couple of requests, if you don't mind, to add to your list of jobs. One is
after the meeting, let's chat about that.
Okay, thank you. I know that you are very busy, so it might not be some time before we can get round to it, but fantastic. Anyway, okay, so thank you everybody. It's been a quite fantastic meeting tonight. Just to let you know, there won't be a meeting in August because some of us will be at Greenbank Observatory taking part in the Eastern Conference. Even if you can't make it to West Virginia, to Greenbank, it's still quite possible to take part in the conference online. In fact, Sarah's doing a brilliant job of using online access to all of its meetings, and I strongly recommend that you have a look and see whether you can take part. And I think it's only about, what's it, about $25, something like that, is it, Ted? I don't know, I can't remember how much it is, but it's only about that sort of price.
I think that's what it was for the online participation.
Yeah, it's substantially cheaper than the face-to-face. So, and if anybody wants to do a presentation at Eastern Conference, I still think they're still fitting a few extras in, I think, at the moment. There might still be room, but you contact me and I'll let you know who you would need to speak to see if there's still space for a presentation.